Hello. Tonight, we'll journey across the emptiness of space to visit our neighboring world, Mars, the red planet. To the naked eye, it appears as a reddish point of light in the night sky, like a distant ember glowing against the darkness. But in reality, it is a world of towering volcanoes and deep canyons, of polar ice caps and ancient riverbeds, of secrets waiting to be uncovered. The light we see from Mars began its journey only minutes ago, traveling at the speed of light across millions of miles of space. Every glimmer we catch carries a message from another world, a place where the sky is pink and the soil is red, where a day lasts just a bit longer than our own. Mars is not just another point of light in the sky. It is our nearest planetary neighbor, the most explored world beyond Earth, and perhaps the most likely place in our solar system where we might one day find evidence of life beyond our own. If you enjoy these calm explorations, you can like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Allow your breathing to slow and your mind to soften, and let the red planet carry you into rest. Let's begin. Mars is the fourth planet from the Sun. Among the 8 planets that orbit our star, Mars holds a special position in the solar system's architecture. It lies approximately 142 million miles away from the Sun on average, though this distance varies as the planet follows its elliptical orbit through space. In astronomical terms, Mars sits at 1.5 astronomical units from our star, meaning it receives less warmth and light than Earth does. This distance places Mars just beyond Earth's orbit, making it one of our closest planetary neighbors. From this position in the solar system, Mars experiences seasons similar to Earth, though they last nearly twice as long due to the planet's longer year. The journey of sunlight from our star to Mars takes about 13 minutes, crossing the void between them at the cosmic speed limit. This moderate distance from the Sun has shaped Mars into the world we observe today, a cold desert planet with a thin atmosphere, yet one that still bears the marks of a warmer, wetter past. Mars is approximately half the diameter of Earth. When we measure Mars from one side to the other, the planet spans about 4,212 miles across, or 6,079 kilometers. Earth, by comparison, stretches nearly 7,918 miles in diameter. If you placed Mars next to Earth, you would see that the red planet is roughly the width of the continent of Africa. Despite being smaller in diameter, Mars possesses a surface area nearly equal to all the dry land on Earth combined. This means that if you could somehow unfold all of Earth's continents and spread them out, they would cover approximately the same area as Mars's entire surface. The planet's modest size gives it only about 11% of Earth's mass, making it a lighter world with weaker gravity. Standing on Mars, you would weigh only 38% of what you weigh on Earth. An adult who weighs 150 pounds on our planet would tip the scales at just 57 pounds on Mars. This reduced gravity would make movement easier, allowing you to jump higher and carry heavier loads, though it would also present challenges for long-term human habitation. A day on Mars lasts slightly longer than an Earth day. As Mars rotates on its axis, a complete turn takes 24 hours and 40 minutes, a period scientists call a sol. This similarity to Earth's day length is one of many features that make Mars familiar to us. The extra 40 minutes might not seem like much, but over time they add up. After living on Mars for just over a month, your internal clock would be nearly a full Earth day ahead of the Martian calendar. This near match with our own day-night cycle would make it easier for human explorers to adapt to life on Mars, as their circadian rhythms would not need dramatic adjustment. The sun rises in the east on Mars, just as it does on Earth, painting the Martian sky with colors that shift from blue near the sun to pink and butterscotch farther away. As the day progresses, the sun arcs across the heavens more slowly than on Earth, taking that extra time to complete its journey from horizon to horizon. When night falls, the stars emerge in a sky free from light pollution, appearing steadier and brighter than they do from Earth's atmosphere-shielded surface. A year on Mars spans 687 Earth days. Mars takes nearly twice as long as Earth to complete one orbit around the Sun, following an elliptical path that brings it closer and farther from our star throughout its year. This extended orbit means that someone who celebrates their 10th birthday on Earth would only have experienced about 5 birthdays if they had been living on Mars instead. The planet's longer year results from its greater distance from the Sun and the slower pace at which it travels along its orbital path. Mars moves through space at about 15 miles per second, a more leisurely pace than Earth's roughly 18.5 miles per second. This extended cosmic journey gives Mars its longer seasons, each lasting roughly twice as long as those on Earth. A Martian summer stretches for months, as does winter, spring, and fall. For future human settlers, this would mean adapting to seasons that last half a year or more, with long periods of cold darkness at the poles and extended growing seasons near the equator during warmer months. The planet is tilted at an angle similar to Earth's. Mars leans at approximately 25 degrees on its axis, just slightly more than Earth's 23.5-degree tilt. This axial tilt is the reason both planets experience seasons. As Mars orbits the Sun, different hemispheres receive more direct sunlight at different times of the year, creating the familiar pattern of summer and winter, spring and fall. Without this tilt, Mars would have no seasons at all, just endless repetition of the same weather patterns day after day. The similarity in tilt between Earth and Mars means that seasonal changes on the red planet follow patterns we can understand. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere endures winter. 6 months later, the situation reverses. However, because Mars's orbit is more elliptical than Earth's, the southern summer is shorter and hotter than the northern summer, while the southern winter is longer and colder. This creates an asymmetry in the seasons that adds another layer of complexity to the Martian climate. Mars is known as the Red Planet. Throughout human history, observers have noticed the distinctive rusty color that makes Mars stand out in the night sky. This reddish hue is not an optical illusion or a trick of distance. It is the genuine color of the Martian surface, visible from millions of miles away. The planet earned its bloody appearance from iron oxide, the same compound that creates rust here on Earth. Billions of years ago, iron in the Martian rocks and soil reacted with oxygen and water, forming a layer of rust that coats much of the planet's surface. Over time, windstorms have lifted this rust into the atmosphere, where it remains suspended as fine dust particles, giving even the Martian sky its characteristic butterscotch and pink tones. Ancient peoples saw this red color and associated the planet with blood, war, and violence. The Romans named it Mars after their god of war, while the ancient Egyptians called it Her-Desha, meaning the Red One. The Babylonians associated it with Nergal, their god of death and pestilence. Across cultures and throughout time, the distinctive color of Mars has captured human imagination and inspired both wonder and dread. The surface of Mars displays many colors beyond red. While the planet's dominant hue is indeed reddish, close-up images from rovers and landers reveal a surprising variety of colors in the Martian landscape. The soil and rocks display shades of brown, gold, tan, and even greenish tones depending on the minerals present and the way sunlight strikes them. Some regions appear almost black, particularly areas covered in basaltic rock from ancient volcanic eruptions. Other locations show lighter patches where dust has settled in thick layers. The polar ice caps shine brilliant white, composed of both water ice and frozen carbon dioxide. In certain lighting conditions, particularly at sunrise and sunset, the Martian surface can take on hues of orange, amber, and copper, creating landscapes that would look both alien and strangely familiar to human eyes. The variety of colors tells geologists stories about the planet's history, revealing where different minerals formed, where water once flowed, and where volcanic activity shaped the terrain. Each shade and tone is a clue in the ongoing investigation of Mars's past and the forces that sculpted its surface into the landscape we see today. Mars has a very thin atmosphere. The Martian atmosphere is incredibly tenuous, with a pressure at the surface averaging only about 0.6% of Earth's atmospheric pressure at sea level. This is roughly equivalent to the air pressure 22 miles above Earth's surface, well into our stratosphere where the air is too thin to breathe. The Martian atmosphere consists primarily of carbon dioxide, making up about 95% of its composition. Nitrogen comprises another 2.6%, argon about 1.9%, and oxygen a mere 0.16%. This thin blanket of gas provides almost no protection from the sun's harsh radiation, no meaningful insulation to retain warmth, and certainly no breathable air for humans or other Earth life. The low atmospheric pressure on Mars means that liquid water cannot exist on the surface for long. When exposed to the Martian air, water either freezes solid or evaporates almost instantly, depending on the temperature. This thin atmosphere is one of the greatest challenges for future human exploration of Mars, requiring any visitors to wear pressurized suits whenever they venture outside their habitats. The average temperature on Mars is extremely cold. Mars is a frozen world, with an average surface temperature hovering around -80 degrees Fahrenheit or -63 degrees Celsius. This bone-chilling cold results from Mars's distance from the Sun, its thin atmosphere which cannot trap heat, and the planet's inability to generate significant internal warmth. However, temperatures on Mars vary dramatically depending on location, time of day, and season. At the equator during a summer afternoon, temperatures can climb to a relatively comfortable 70 degrees Fahrenheit, though they plummet to -100 degrees Fahrenheit or colder at night. The polar regions, covered in ice and shrouded in darkness during winter, can reach temperatures as low as -225 degrees Fahrenheit. This extreme cold would flash freeze exposed human skin in seconds and turn the air itself deadly. The thin atmosphere means that temperature differences can be dramatic, even over short distances. At noon on the equator, the ground might be warm enough to support liquid water, while the air just a few feet above remains well below freezing. This creates a strange environment where your feet could feel spring-like warmth while your head experiences winter's deep freeze. Mars has weak gravity compared to Earth. The gravitational pull at the surface of Mars is only about 38% as strong as Earth's gravity. This reduced gravity results from Mars's smaller mass and size. While Earth pulls on objects at 9.8 meters per second squared, Mars exerts a force of only 3.7 meters per second squared. For anyone visiting Mars, this weaker gravity would have profound effects on daily life. Activities that require effort on Earth would become easier. You could jump nearly 3 times higher than on Earth. Lifting heavy objects would feel effortless. Running and walking would take less energy, though you would need to adjust your gait to avoid bounding uncontrollably with each step. However, this reduced gravity would also present challenges. Bones and muscles would gradually weaken without the constant resistance of Earth's stronger pull. Blood would distribute differently in the body, potentially causing health problems. Scientists studying the effects of reduced gravity on human health have found that astronauts on the International Space Station, which simulates weightlessness, experience bone loss, muscle atrophy, and changes in cardiovascular function. The same challenges would face Mars colonists, requiring constant exercise and possibly artificial gravity systems to maintain health over long periods. The planet has a dense iron core. Deep inside Mars, at the planet's center, lies a core composed primarily of iron, with significant amounts of nickel and sulfur mixed in. This metallic heart of Mars measures between 930 and 1,300 miles in radius, making it roughly half the size of the entire planet. Recent seismic data from NASA's InSight lander suggests that this core is at least partially liquid, with iron and nickel still in molten form despite the planet's age. The presence of sulfur in the core, more abundant than in Earth's core, has important implications for Mars's magnetic field, or rather, its lack thereof. On Earth, the movement of molten iron in the outer core generates our planet's protective magnetic field. Mars once had a similar magnetic shield, evidenced by remnant magnetic fields frozen into ancient rocks in the southern highlands. But billions of years ago, Mars's core cooled enough that the dynamo shut down, and the planet lost its global magnetic field. Without this protective shield, the solar wind could strip away much of the Martian atmosphere, gradually transforming Mars from a warmer, wetter world into the cold desert we see today. Mars is surrounded by a rocky mantle. Encircling the iron core is a layer of rock called the mantle, extending from about 770 to 1,070 miles thick. This mantle, composed of silicate rocks rich in iron and magnesium, makes up the bulk of Mars's volume. Unlike Earth's mantle, which flows and convects, driving plate tectonics and volcanic activity, Mars's mantle appears to be largely inactive today. The lack of significant mantle convection means that Mars does not have plate tectonics like Earth. The planet's crust remains fixed in place, rather than moving around in great plates. This has profound implications for the planet's geological history. Without plate tectonics to recycle the crust, Martian volcanoes could remain over the same spot for billions of years, allowing them to grow to enormous sizes. The same hotspots that fed lava to the surface could keep erupting in the same location for eons, building up massive volcanic mountains that dwarf anything on Earth. The mantle's reduced activity also means that Mars lacks many of the geological renewal processes that keep Earth's surface relatively young and dynamic. The Martian crust varies in thickness. Above the mantle lies the planet's outermost layer, the crust, which ranges from about 6 to 30 miles thick. This rocky shell, composed primarily of basaltic rock similar to Earth's ocean floors, shows significant variation across the planet. The southern highlands have a thicker, older crust, heavily cratered from billions of years of meteorite impacts. The northern lowlands have a thinner, younger crust that sits several miles lower in elevation. This difference between north and south, called the Martian dichotomy, is one of the most striking features of the planet when viewed from space. Scientists debate what caused this dramatic difference. Some theories suggest a giant impact early in Mars's history could have blasted away much of the northern hemisphere's crust. Others propose internal processes, perhaps related to ancient mantle convection, created the divide. Whatever the cause, this dichotomy gives Mars a strangely lopsided appearance, with nearly the entire northern third of the planet sitting in a vast, smooth depression, while the southern 2/3 rises higher, rough and ancient. Mars has 2 small moons. Orbiting the red planet are 2 tiny, irregularly shaped satellites named Phobos and Deimos. These moons, discovered in 1877 by American astronomer Asaph Hall, bear the names of the Greek gods of fear and panic, appropriate companions for the god of war. Phobos, the larger of the 2, measures only about 14 miles across at its widest point, while Deimos spans a mere 8 miles. Both moons are dark and heavily cratered, resembling asteroids more than the large spherical moon that orbits Earth. Their origin remains a matter of scientific debate, with several competing theories. They may be asteroids that wandered too close to Mars and were captured by its gravity, though their near-circular equatorial orbits make this scenario challenging to explain. Alternatively, they might have formed from debris blasted into orbit when a large object struck Mars early in its history, similar to the leading theory for how Earth's moon formed. Or they could be remnants of a larger moon that was torn apart by tidal forces. Whatever their origin, Phobos and Deimos offer unique observing platforms for studying Mars from nearby, and they may serve as waypoints for future human missions to the red planet. Phobos orbits extremely close to Mars. Of all the moons in the solar system, Phobos holds the record for orbiting closest to its planet. It circles Mars at an altitude of just 3,700 miles above the surface, far closer than our moon, which sits 238,000 miles from Earth. This proximity means that Phobos completes an orbit in only 7 hours and 39 minutes, racing around Mars 3 times each Martian day. From the surface of Mars, Phobos would rise in the west and set in the east, appearing to move backward across Mars. The sky compared to the normal direction of celestial motion. The moon would zip across the heavens in just over 4 hours, a strange sight for anyone accustomed to watching Earth's moon take hours to rise or set. The tidal forces from Mars are gradually pulling Phobos closer to the planet at a rate of about 6 feet per century. In approximately 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces when it crosses the Roche limit, the distance at which tidal forces overcome the moon's own gravity. When this happens, the debris may form a temporary ring around Mars, giving the red planet a feature currently found only around the giant outer planets. Deimos orbits farther from Mars and moves more slowly. The smaller of Mars's 2 moons, Deimos, follows a more distant orbit about 14,180 miles from the planet's surface. At this distance, Deimos takes just over 30 hours to complete one orbit, moving only slightly faster than Mars rotates. From the Martian surface, Deimos would rise in the east and set in the west, like Earth's moon, but would take about 2.7 days to cross from one horizon to the other. The moon would appear as little more than a bright star, showing no discernible disk to the naked eye. Unlike Phobos, which is spiraling inward toward its doom, Deimos is slowly drifting away from Mars, pushed outward by tidal forces, in the same way Earth's moon is gradually receding from our planet. Eventually, perhaps billions of years in the future, Deimos may escape from Mars entirely, wandering off to become its own independent object orbiting the Sun. For now, though, it remains a loyal companion to the red planet, a tiny world of its own with landscapes that may never be seen up close by human eyes. Both moons are irregularly shaped and heavily cratered. Phobos and Deimos lack the spherical form of larger moons, instead resembling lumpy potatoes or misshapen rocks. Their small size means their gravity is too weak to pull them into round shapes, leaving them with the irregular forms they acquired when they first coalesced. Both moons are covered in craters from countless impacts over billions of years. Phobos bears a particularly dramatic scar, a crater called Stickney, that measures 5.6 miles across, nearly half the width of the Moon itself. This impact must have come close to shattering Phobos entirely, and grooves radiating from Stickney suggest the shock waves from the impact traveled through the Moon's interior. The surfaces of both moons are grey and remarkably dark, reflecting only about 7% of the sunlight that strikes them. They are among the darkest objects in the solar system, likely due to their composition of carbon-rich material similar to certain types of asteroids. Dust covers their surfaces to surprising depths, despite their weak gravity. This regolith, as the loose surface material is called, could provide raw materials for future space missions, offering resources that could be used to produce fuel or building materials. Mars likely had a global magnetic field billions of years ago. When Mars was young, it generated a magnetic field similar to Earth's, created by the movement of molten iron in its core. This magnetic shield extended far into space, deflecting the solar wind and protecting the planet's atmosphere from being stripped away. Evidence for this ancient field comes from rocks in the southern highlands that preserved magnetic signatures as they cooled billions of years ago, like tape recordings frozen in stone. These remnant magnetic fields are surprisingly strong, suggesting that young Mars had a magnetic field perhaps even stronger than Earth's current field. But approximately 4 billion years ago, something changed. The Martian core cooled, the dynamo shut down, and the global magnetic field collapsed. Without this protective shield, the solar wind could interact directly with the upper atmosphere, gradually stripping it away into space. Over hundreds of millions of years, Mars lost much of its atmosphere, and with it, the ability to maintain liquid water on its surface. This loss of magnetic protection may have been one of the key events that transformed Mars from a potentially habitable world into the frozen desert we see today. The southern highlands are heavily cratered and ancient. The southern hemisphere of Mars rises several miles higher than the northern lowlands and bears the scars of billions of years of meteorite bombardment. This region, covering roughly 2/3 of the planet, represents some of the oldest terrain in the solar system, dating back more than 4 billion years to a period called the Noachian era. The abundance of impact craters in the southern highlands tells us that this surface has remained largely unchanged since that ancient time. Each crater represents a collision with an asteroid or comet, and the overlapping of countless craters creates a landscape of remarkable complexity. Some of these impact basins span hundreds of miles. The Hellas Planitia Basin, for instance, stretches about 400 miles across and plunges more than 4 miles deep, making it one of the largest impact structures in the solar system. The heavily cratered southern highlands stand in stark contrast to the smoother northern lowlands. And this dramatic difference between the two hemispheres remains one of Mars's most intriguing mysteries. The northern lowlands are smooth and low-lying. Nearly the entire northern third of Mars sits in a vast depression several miles below the average elevation of the planet. This region, called Vastitas Borealis, is remarkably smooth compared to the cratered southern highlands, with far fewer impact craters and much younger terrain. The surface here shows signs of having been resurfaced relatively recently in geological terms, perhaps within the last 3 billion years. Some scientists believe this enormous basin once held an ocean, a theory supported by features that resemble ancient shorelines, sedimentary deposits that suggest water-laid layers, and the overall geography that would naturally collect water flowing from higher elevations. The northern lowlands are not perfectly flat. They contain scattered volcanic features, buried impact craters, and large regions of polygonal terrain that suggest the presence of ground ice. During winter, much of this region becomes covered with carbon dioxide frost that sublimates away when spring returns. The stark difference in elevation and character between the northern lowlands and southern highlands creates one of the most dramatic geological contrasts of any planet in the solar system. Olympus Mons is the largest volcano in the solar system. Rising from the Martian surface like a monument to the planet's volcanic past stands Olympus Mons, the tallest known mountain in the solar system. This colossal shield volcano towers about 16 miles above the surrounding plains, nearly 3 times the height of Mount Everest. If you could place Olympus Mons on Earth, it would reach well into the stratosphere, its summit poking above most of our atmosphere. The volcano stretches roughly 374 miles across its base, approximately the size of the state of Arizona. This immense breadth means that if you were standing on the slopes of Olympus Mons, you could not see the summit, as it would lie beyond the horizon. The volcano's slopes are remarkably gentle, averaging only about 5 degrees, making it technically hikeable, though the climb would take days or weeks. At the summit sits a complex of 6 overlapping calderas, collapsed craters formed when magma chambers emptied during eruptions. The youngest lava flows on Olympus Mons appear to be only about 25 million years old, suggesting this giant may still be capable of erupting, though it has lain dormant throughout the entire span of human existence. The sheer size of Olympus Mons exists because Mars lacks plate tectonics. On Earth, volcanic hotspots move relative to the crust due to plate tectonics. The Hawaiian Islands, for example, formed as the Pacific Plate moved over a stationary hotspot, creating a chain of volcanoes rather than a single giant one. Mars, being smaller than Earth and cooling more quickly, does not have active plate tectonics. Its crust remains stationary. When a volcanic hotspot formed beneath the Martian surface, it could keep erupting in the same spot for billions of years, slowly building up a massive mountain layer by layer. Olympus Mons may have been active for hundreds of millions of years, perhaps even billions, allowing it to grow to its tremendous size. The volcano is supported by a crust that appears to be about 45 miles thick at this location, providing a stable platform for this immense weight. The base of Olympus Mons is surrounded by a cliff up to 6 miles high in places, possibly created by massive landslides or the collapse of the volcano's flanks under their own enormous weight. Valles Marineris is a vast canyon system stretching across the face of Mars near its equator. Lies Valles Marineris, the grandest canyon in the solar system. This enormous system of interconnected canyons extends more than 2,500 miles from end to end, roughly the width of the United States from Los Angeles to New York. At its widest, The canyon system reaches 120 miles across, and in places it plunges to depths of 4 miles below the surrounding terrain. By comparison, Earth's Grand Canyon measures only 277 miles long, 18 miles across at its widest, and about 1 mile deep. Valles Marineris is so large that if you placed it on Earth, it would stretch from San Francisco to New York City. And if you stood on one rim, the opposite side would lie far beyond the horizon. The canyon system likely formed not through erosion by water like the Grand Canyon, but through tectonic forces related to the formation of the nearby Tharsis volcanic region. As Tharsis rose billions of years ago, the surrounding crust was stretched and fractured, creating vast rifts that eventually became the canyons we see today. Over time, these initial fractures were widened and deepened by landslides, erosion from whatever water was present, and the collapse of underground ice and groundwater. The canyon system shows evidence of water in its past. While Valles Marineris formed primarily through tectonic cracking, water has clearly played a role in shaping and enlarging the canyons. The eastern end of the canyon system opens into chaotic terrain characterized by jumbled blocks of rock and signs of massive flooding. These outflow channels suggest that enormous volumes of water once burst from underground, possibly when volcanic heating melted subsurface ice, creating floods that dwarfed anything ever seen on Earth. Within the canyons themselves, layered deposits on the floors might be sediments that settled out from lakes that once filled portions of the canyon system. Some of these layers show signs of sulfate minerals that typically form when water evaporates, leaving behind dissolved salts. The walls of the canyons display features that resemble channels carved by flowing water or seeps. Together, these clues paint a picture of a time when water was much more active in Valles Marineris, flowing through and possibly ponding within these great rifts, slowly modifying their shape through erosion and deposition. Mars has abundant impact craters of all sizes. The surface of Mars is pockmarked with impact craters ranging from tiny pits a few feet across to massive basins spanning hundreds of miles. Scientists have catalogued more than 43,000 craters, with diameters of at least 3 miles, and countless smaller ones pepper every region of the planet. Each crater tells a story of a violent collision with an asteroid or comet, events that have shaped the Martian surface for billions of years. The size and distribution of craters help geologists determine the age of different regions. Areas with many craters overlapping each other must be ancient, having accumulated impacts over billions of years. Regions with few craters are relatively young, suggesting that something has resurfaced the area more recently, perhaps lava flows or sediment deposition. Some Martian craters show unique features not seen on airless bodies like the Moon. Many display fluidized ejector blankets, where the material thrown out by the impact appears to have flowed like mud rather than scattering as dry debris. This suggests the ground contained ice or water at the time of impact, which was melted by the heat of the collision. The Hellas Basin is one of the largest impact structures in the solar system. In the southern highlands of Mars lies Hellas Planitia, an impact basin so large and deep it dominates the entire region. This enormous crater measures about 1,400 miles across and plunges more than 4 miles below the surrounding terrain. The impact that created Hellas must have been catastrophic, likely occurring more than 4 billion years ago when Mars was still young. An asteroid perhaps 60 miles across would have been needed to blast out such a massive crater, and the collision would have sent shock waves rippling through the entire planet. The basin floor, being one of the lowest points on Mars, experiences higher atmospheric pressure than most of the planet, and temperatures here can be relatively warm by Martian standards. In summer, afternoon temperatures in Hellas might reach above freezing. The basin often fills with dust during planet-wide dust storms, and in winter, frost coats its floor. Looking at Hellas from space, you can see how the impact fractured the surrounding terrain, creating radial patterns of cracks and grooves that extend for hundreds of miles from the basin's edge. The Tharsis region hosts several enormous volcanoes. In Mars's western hemisphere rises the Tharsis Bulge, a massive volcanic province that dominates the planet's topography. This region, stretching about 2,500 miles across and rising several miles above the surrounding terrain, contains 4 of the largest volcanoes in the solar system: Olympus Mons, Ascraeus Mons, Pavonis Mons, and Arsia Mons. These shield volcanoes were built by countless lava flows over hundreds of millions, or perhaps billions of years. The formation of Tharsis had profound effects on Mars. The immense weight of volcanic rock piled miles thick may have actually tipped the planet's rotation axis, causing the poles to shift position relative to the surface. This change would have completely altered Mars's climate patterns, redirecting wind patterns and possibly relocating the regions where ice accumulated. The volcanic activity in Tharsis also released enormous volumes of gas into the atmosphere, perhaps creating a thicker atmosphere than Mars has today. Around Tharsis, the crust has been stretched and fractured by the rising of hot material from below, creating the system of canyons we now call valles marineris. Evidence suggests Mars once had flowing water on its surface. Perhaps the most significant discovery about Mars in the past few decades is the overwhelming evidence that liquid water once flowed across its surface. Ancient river valleys carved into the terrain, delta formations where rivers emptied into lakes or seas, layered rock that appears to be sediment deposited by water, minerals that can only form in the presence of liquid water. These clues and many more tell us that Mars was once a very different world, one where water shaped the landscape just as it does on Earth today. The rivers on Mars were not small streams. Some outflow channels suggest floods of staggering scale, with volumes of water that dwarf even Earth's largest floods. These floods may have been triggered when volcanic heat melted underground ice, releasing the water in catastrophic bursts. Other features suggest more persistent water flow, with rivers that flowed for thousands or even millions of years. The presence of ancient lakes and possible ocean basins indicates that water could accumulate and remain on the surface for geologically significant periods, creating environments where life, if it ever arose, might have thrived. Ancient riverbeds are visible across the Martian surface. Scattered across Mars, particularly in the ancient southern highlands, are vast networks of valleys that look remarkably like dried-up river systems on Earth. These valley networks branch and merge in the characteristic patterns of water-carved channels, starting narrow at their upper ends and growing wider as they flow downhill toward lower elevations. Some valleys show features like meanders and braided channels that strongly suggest flowing water. These ancient riverbeds are incredibly old, dating back more than 3.7 billion years to a time called the Noachian period, when Mars's climate was apparently warmer and wetter than today. The valleys often originate in crater rims and highland regions, suggesting precipitation, rain or snow that fell from Martian skies and then flowed downhill, gradually carving channels into the rock. Over time, this water made its way to the northern lowlands, where it may have collected into lakes or a northern ocean. The preservation of these ancient river valleys tells us that Mars's climate changed dramatically billions of years ago, from a world where water could flow on the surface to the frozen desert we see today. Scientists have found evidence of ancient lake beds. In several locations on Mars, rovers and orbiters have found compelling evidence for ancient lakes that once filled impact craters and low-lying areas. Gale Crater, where the Curiosity rover has been exploring since 2012, shows clear signs of having hosted a lake that persisted for perhaps millions of years. The rover has found sedimentary rocks containing minerals that form in water, rounded pebbles that were likely smoothed by tumbling in streams, and layered deposits that suggest sediments settling out of standing water. Similarly, Jezero Crater, now being explored by the Perseverance rover, contains what appears to be an ancient river delta where a stream emptied into a lake, depositing layers of sediment that are now preserved in rock. These lake beds are exciting targets in the search for ancient Martian life, because on Earth, lakes and deltas are excellent environments for preserving fossils and chemical signatures of life. If microorganisms ever existed in Martian waters, their remains might still be found in the sediments of these ancient lake beds. Evidence suggests Mars may have had oceans in its northern hemisphere. Perhaps one of the most debated questions about ancient Mars is whether it once had an ocean covering much of the northern lowlands. Several lines of evidence have led some researchers to this possibility. The northern lowlands lie several miles below the average elevation of the planet, forming a natural basin where water would naturally collect. Features that some scientists interpret as ancient shorelines have been identified, though the scientific community continues to discuss whether these truly represent marks left by standing water. Sedimentary deposits in the northern plains suggest materials that could have been laid down in water and later compressed into rock. Some researchers have identified what they interpret as possible tsunami deposits, massive accumulations of debris that might have formed when asteroid impacts struck a Martian ocean, generating enormous waves. If Mars did have an ocean, it would have required a much thicker atmosphere than exists today to prevent the water from freezing or evaporating. This suggests that young Mars may have had atmospheric pressure, perhaps approaching Earth's, providing a much more clement environment than the hostile conditions that prevail today. Mars's climate has changed dramatically over time. The evidence for ancient water on Mars tells us that the planet's climate must have been very different billions of years ago. To support liquid water on the surface, Mars would have needed a thicker atmosphere to maintain sufficient pressure and temperature. Based on computer models and geological evidence, some scientists estimate that young Mars might have had an atmosphere substantially thicker than it has today, with enough greenhouse warming from carbon dioxide and other gases to keep the surface above freezing at least seasonally. Over time, this atmosphere was gradually lost through multiple processes. Without a magnetic field to protect it, the solar wind could strip away atmospheric gases. Volcanic activity, which could have replenished the atmosphere, eventually slowed and nearly ceased. Major impacts might have blasted atmosphere into space. The lighter gravity of Mars made it easier for gases to escape compared to Earth. By about 3.5 billion years ago, Mars appears to have largely transformed into the cold, dry world we see today, with only occasional periods of water activity as volcanic heat, melted subsurface ice, or climate variations temporarily warmed the surface. The polar ice caps are composed of water ice and carbon dioxide. At both of Mars's poles sit permanent ice caps that grow and shrink with the seasons. These polar caps are layered structures composed primarily of water ice mixed with dust, covered by varying amounts of carbon dioxide ice. During winter, temperatures at the poles plunge so low that carbon dioxide from the atmosphere freezes directly onto the ground, adding a seasonal layer of dry ice several feet thick. This seasonal cap can extend much farther from the pole than the permanent cap underneath. In spring, the carbon dioxide ice sublimes back into gas, revealing the permanent water ice cap below. The North Polar Cap, which is less contaminated with dust than the South, appears brilliant white and measures about 600 miles across. If you could melt all the ice in both polar caps, it would cover Mars with water about 60 feet deep. The layered nature of the ice, visible in images of exposed cliff in the polar regions, suggests that Mars's climate has varied over millions of years, with different layers forming during different climatic conditions. Seasonal frost covers large areas during winter. As winter approaches in each hemisphere, frost begins to spread from the poles toward the equator, eventually covering up to 1/3 of the planet's surface. This frost consists primarily of carbon dioxide, though water frost also forms in some areas. The seasonal frost appears bright white against Mars's reddish soil, creating a stark contrast visible even through telescopes on Earth. As spring arrives, the frost begins to sublime, turning directly from solid to gas without melting. This sublimation often creates interesting patterns, particularly in areas where dark spots or streaks appear on sandy slopes, possibly formed when the subliming carbon dioxide gas carries darker material downhill. The advance and retreat of seasonal frost is one of the most dramatic seasonal changes on Mars, transforming the appearance of large regions and affecting atmospheric pressure across the planet as carbon dioxide freezes out of and returns to the atmosphere. Mars has planet-wide dust storms. Perhaps the most dramatic weather phenomenon on Mars is the occasional development of dust storms that can engulf the entire planet. These global dust storms are rare, occurring roughly every 3 Martian years on average, though the timing is unpredictable. They typically begin in the southern hemisphere during southern summer, when Mars is closest to the Sun and heating is most intense. Small dust storms merge and grow, eventually spreading dust throughout the atmosphere and blocking out the Sun for weeks or even months. During the 2018 global dust storm, skies over Gale Crater, where the Curiosity rover operates, became so dark that it looked like nighttime even during midday. The Opportunity rover, which relied on solar power, could not generate enough electricity to survive and eventually ceased operation. These dust storms dramatically affect Mars's atmosphere and surface, redistributing dust around the planet, heating the upper atmosphere while cooling the surface, and affecting pressure patterns that influence weather for months afterward. The dust particles on Mars are extremely fine. The dust that gives Mars its characteristic color and fills its atmosphere during dust storms consists of incredibly fine particles, much smaller than grains of sand. These particles, averaging only about 3 microns in diameter, roughly half the width of a human hair, can remain suspended in the thin Martian atmosphere for long periods. This fine dust is the product of billions of years of weathering, as rocks have been ground down by wind, temperature changes, and occasional water action. The dust is rich in iron oxide minerals, which give it the reddish color, but also contains silica, aluminum, magnesium, and other elements. For future human explorers, this fine dust will present significant challenges. It can infiltrate equipment, scratch optics and solar panels, and may be hazardous if inhaled. The dust easily clings to surfaces through electrostatic forces, making it difficult to remove. Keeping spacesuits, habitats, and equipment clean of dust will be one of the many challenges of living and working on Mars. Wind has shaped much of the Martian landscape. Although Mars's atmosphere is thin, winds can still reach high velocities, and over billions of years, these winds have sculpted the surface in distinctive ways. Sand dunes march across the floors of impact craters and between rocky outcrops. Yardangs, streamlined ridges carved by wind, point in the direction of prevailing winds. Dark streaks on slopes mark where dust devils have cleaned the surface, revealing darker material underneath. Large regions of the planet show wind-etched patterns and erosion that has slowly worn away rock over eons. During dust storms, winds can reach speeds of 60 miles per hour or more, though the thin atmosphere means these winds exert less force than similar wind speeds would on Earth. Still, they can lift dust particles into the air, where they are carried for hundreds or thousands of miles before settling elsewhere. This continual movement of dust gradually polishes rocks, fills in craters, and redistributes material across the planet's surface, slowly but constantly changing the landscape in ways that would take much longer on airless bodies like the Moon. The Martian sky is typically butterscotch or pink. Standing on Mars and looking up, you would not see the familiar blue sky of Earth. During most times of the day, the Martian sky appears reddish tan or butterscotch, a color caused by fine dust particles suspended in the atmosphere. These dust particles scatter light differently than the nitrogen and oxygen molecules that dominate Earth's atmosphere. Blue light scatters forward, so the area around the Sun appears bluish, while the rest of the sky takes on those distinctive rusty tones. At sunrise and sunset, the situation reverses from what we see on Earth. While Earth's sky turns red at these times, Mars's sky becomes blue around the Sun and redder farther away. This beautiful inversion creates sunsets and sunrises of extraordinary beauty, with a bluish glow surrounding the Sun as it approaches the horizon. Cameras on various Mars landers and rovers have captured these stunning views, giving us glimpses of what it would be like to watch the day begin and end on another world. Surface pressure on Mars varies with the seasons. The atmospheric pressure at Mars's surface changes significantly throughout the year as carbon dioxide freezes out at the winter pole and sublimes back into the atmosphere at the summer pole. During northern winter, for instance, about 25 to 30% of Mars's entire atmosphere freezes onto the southern ice cap. This causes atmospheric pressure to drop noticeably across the entire planet. In spring, this carbon dioxide returns to the atmosphere and pressure rises again. This seasonal breathing of the atmosphere is unique among the planets. The varying pressure affects winds, dust storm activity, and the possibility of liquid water existing on the surface, if only briefly. At its highest, surface pressure on Mars reaches only about 8 to 10 millibars in the deepest parts of the Hellas Basin. At its lowest, in winter at high elevations, pressure may drop to only 4 millibars. These pressures are so low that any exposed liquid water would rapidly evaporate or freeze, making liquid water inherently unstable on the Martian surface under current conditions. Curiosity and Perseverance are exploring Mars right now. 2 car-sized rovers are currently driving across the Martian surface, examining rocks, drilling into the ground, and sending back detailed information about the red planet. Curiosity, which landed in Gale Crater in August 2012, has been exploring for more than a decade, far exceeding its original 2-year mission. The rover has climbed partway up Mount Sharp, a mountain of layered sediments in the center of the crater, finding evidence of ancient lakes and discovering complex organic molecules preserved in rocks. Perseverance, which landed in Jezero Crater in February 2021, is specifically searching for signs of ancient microbial life, while also collecting and caching rock samples for potential future return to Earth. Both rovers are powered by radioactive plutonium that generates electricity through heat, allowing them to operate through dust storms and Martian winter, when solar-powered spacecraft would fail. They move slowly, often traveling only a few dozen yards per day, carefully choosing their paths and stopping frequently to examine interesting rocks with their suite of scientific instruments. Perseverance has collected samples for potential return to Earth. One of Perseverance's primary missions is to collect and cache rock and soil samples that could be returned to Earth by a future mission. As of late 2020, the rover has drilled and sealed more than 20 samples in special tubes designed to preserve them for years. These samples include rocks that appear to have formed in water, sediments from the ancient delta, and rocks that show intriguing features that might, possibly, be related to ancient microbial life. The samples are being stored both on the rover and at a depot on the surface, where they wait for a future sample return mission that may arrive in the 2030s. Once these samples reach Earth, they can be analyzed with sophisticated instruments that are too large and complex to send to Mars. Scientists hope these samples will help answer fundamental questions about Mars's past climate, whether it ever hosted life, and when and how it transformed from a warmer, wetter world to the frozen desert we see today. Ingenuity became the first aircraft to fly on another planet. Strapped to Perseverance's belly during the journey to Mars was a small helicopter called Ingenuity, designed to test whether powered flight was possible in Mars's thin atmosphere. In April 2021, Ingenuity made history by completing the first powered, controlled flight on another world. The helicopter, weighing only about 4 pounds, had to spin its rotors at 2,400 revolutions per minute to generate enough lift in the thin Martian air. Over the course of its mission, Ingenuity completed some 2 flights, far exceeding its original plan of just 5 test flights. The little helicopter scouted routes for Perseverance, photographed areas the rover could not reach, and demonstrated that aerial exploration of Mars is feasible. Ingenuity eventually sustained damage to its rotor blades during a landing, ending its flight operations, but it proved that future missions could include helicopters or even larger aircraft to explore Mars from the air, reaching places that rovers cannot go and covering distances much faster than ground vehicles. Many spacecraft have been sent to Mars. Over the past 6 decades, humanity has sent more than 40 missions toward Mars, though not all have succeeded. The first successful flyby occurred in 1965, when NASA's Mariner 4 sent back the first close-up images of the Martian surface, revealing a cratered, moon-like landscape that shocked scientists who had hoped to see canals and perhaps even vegetation. Since then, orbiters have mapped the planet in exquisite detail. Landers have touched down at diverse locations, and rovers have driven many miles across the surface. The Soviet Union attempted numerous missions in the 1960s and 70s, but faced disappointing failures. NASA has had the most success, with Mars missions including Vikings 1 and 2, which were the first to successfully operate on the surface in the 1970s, the Mars Pathfinder with its small Sojourner rover in 1997, the long-lived Opportunity and Spirit rovers, and the current Curiosity and Perseverance missions. Other space agencies have also reached Mars, with Europe's Mars Express orbiter operating since 2003, India's Mars Orbiter mission arriving in 2014, and China's Tianwen-1 mission placing both an orbiter and a rover on Mars in 2021. Mars has an orbital period that nearly matches Earth's synodic period. Launch opportunities to Mars occur roughly every 26 months when Earth and Mars align favorably in their orbits. These launch windows are critically important because attempting to reach Mars at other times would require far too much fuel. During these windows, spacecraft can follow a path called a Hohmann transfer orbit, an energy-efficient trajectory that takes advantage of the planet's orbital mechanics. The journey typically takes between 6 and 8 months, during which the spacecraft travels more than 300 million miles through space. As Mars and Earth move in their respective orbits, the distance between them varies dramatically. At their closest approach, called opposition, Mars can come within about 35 million miles of Earth, while at their farthest separation, they can be more than 250 million miles apart. This variation in distance affects not only travel times, but also communication delays and the amount of detail we can see through telescopes from Earth. Robotic missions have prepared the way for potential human exploration. The decades of robotic exploration have taught us crucial lessons about Mars that will inform future human missions. We have learned about the Martian climate, how dust storms develop, and what resources are available on the planet. We have identified hazards like the fine, clingy dust and the intense radiation from space that reaches the surface unimpeded by Mars's thin atmosphere and lack of magnetic field. We have tested technologies like precision landing, generating oxygen from atmospheric carbon dioxide, and long-duration operations in the Martian environment. Perhaps most importantly, we have discovered that water ice is abundant beneath the surface at higher latitudes, providing a potential resource for future human explorers. The knowledge gained from robotic missions has transformed Mars from a mysterious light in the sky to a world we understand well enough to envision sending humans there, though many challenges remain to be solved before such missions become feasible. No human has yet set foot on Mars. Despite decades of robotic exploration and countless science fiction stories about Mars, no person has ever traveled to the Red Planet. The challenges of sending humans to Mars are formidable. The journey would take at least 6 to 8 months each way, exposing astronauts to cosmic radiation and the health effects of prolonged weightlessness. Once on Mars, explorers would need to survive in an environment with no breathable air, temperatures averaging far below freezing, and only weak sunlight for solar power. They would need protection from radiation, a reliable source of water, food production capabilities for a mission lasting 2 to 3 years, and the ability to manufacture fuel for the return journey. Despite these challenges, multiple space agencies and private companies are actively working toward human missions to Mars, with potential timelines suggesting the 2030s or 2040s as realistic goals. When humans finally do reach Mars, it will represent one of humanity's greatest achievements, fulfilling a dream that has captivated us for generations. Mars features heavily in science fiction and popular culture. Perhaps no other planet has captured human imagination as thoroughly as Mars. From the late 19th century onwards, Mars has been the setting for countless novels, films, and stories. H.G. Wells's The War of the Worlds depicted an invasion from Mars, shaping public perception of Martians for generations. Edgar Rice Burroughs wrote adventure stories set on Mars populated by exotic civilizations. Ray Bradbury's The Martian Chronicles explored themes of colonization and cultural contact. More recently, films like The Martian have offered realistic portrayals of survival on the Red Planet. This cultural fascination stems partly from Mars being the most Earth-like of the planets, the one place in our solar system where we can most easily imagine humans living and working. The color red has also contributed to Mars's mystique, making it stand out in the night sky and leading ancient cultures to associate it with blood and warfare. Today, Mars continues to inspire not just stories but serious plans for actual human exploration and potential colonization. the search for life on Mars continues. One of the primary drivers of Mars exploration is the question of whether life ever arose on the red planet. With its ancient lakes and rivers, its organic molecules preserved in rocks, and its potential for subsurface water today, Mars offers tantalizing possibilities. Current and planned missions are specifically designed to search for biosignatures, evidence that life existed in the past or perhaps still exists in protected niches underground. The Perseverance rover is examining rocks that formed in water, looking for patterns or structures that might have been created by microorganisms. Future sample return missions will allow scientists to examine Martian rocks with the most sophisticated instruments available on Earth. Missions to Mars's polar regions or subsurface environments might find liquid water where microbial life could survive today. The question of whether we are alone in the universe may ultimately be answered by the rocks and soil of our neighboring planet, making the search for life on Mars one of the most important scientific endeavors of our time. Evidence of organic molecules has been found on Mars. Among the most exciting discoveries on Mars in recent years is the detection of organic molecules, the complex carbon-based compounds that are the building blocks of life. The Curiosity rover has found a variety of organic molecules in rocks that are 3 billion years old, including complex chains and rings of carbon atoms bonded with other elements. These molecules could have formed through biological processes if life ever existed on Mars, but they might also have formed through geological processes or been delivered by meteorites falling from space. Determining the origin of these organic molecules is one of the great challenges in Mars exploration. Recently, Perseverance discovered a rock nicknamed Chayava Falls that contains organic molecules along with unusual mineral features that, in some Earth contexts, might suggest microbial activity. However, scientists emphasize that these features could also form through non-biological processes, and extraordinary claims require extraordinary evidence. Much more analysis will be needed, ideally with samples returned to Earth, before any definitive conclusions can be drawn about whether these features indicate past life on Mars. Mars may still have liquid water underground. While liquid water is unstable on Mars's cold, low-pressure surface, conditions underground could be very different. Geothermal heat from the planet's interior might maintain temperatures above freezing at depth, and the pressure of overlying rock would prevent water from evaporating or boiling. Some radar observations from Mars orbiters have detected features that researchers have interpreted as possible. Subsurface lakes of liquid water beneath the southern ice cap, though these findings remain subjects of active scientific debate. If such water exists, it could potentially harbor living microorganisms, making Mars's subsurface one of the most intriguing targets in the search for life beyond Earth. Future missions may attempt to drill deep enough to reach these suspected water reservoirs, though the technical challenges of drilling on Mars are substantial. The possibility that Mars harbors subsurface aquifers adds another layer of complexity to our understanding of the planet and raises fascinating questions about whether life could persist in such environments. Mars is visible to the naked eye from Earth. On most clear nights, when Mars is in the right position in its orbit, you can look up and see the red planet with no optical aid whatsoever. Mars appears as a distinctly reddish point of light, brighter than most stars and noticeably colorful. During favorable oppositions, when Mars and Earth are particularly close, the planet can shine brilliantly in the sky, becoming one of the brightest objects visible after the Sun, Moon, and Venus. Ancient peoples were intimately familiar with Mars's movements across the sky, tracking how it wandered through the constellations over months and years. The planet's apparent retrograde motion, when it seems to move backward relative to the stars, puzzled early astronomers and played a crucial role in the development of our understanding of planetary motions. Today, with even small telescopes or binoculars, you can see Mars as a tiny disk and, during close approaches, possibly make out some surface features like the dark region of Syrtis Major or the bright gleam of the polar ice caps. Mars's orbit is noticeably elliptical. Among the planets in our solar system, Mars has the second most eccentric orbit after Mercury. This means its distance from the Sun varies considerably during its year, ranging from about 128 million miles at closest approach, called perihelion, to about 155 million miles at its farthest, called aphelion. This variation affects Mars's climate significantly. Southern summer occurs when Mars is closest to the Sun, making southern summers shorter but more intense than northern summers. The southern hemisphere can get significantly warmer than the northern hemisphere at their respective summer peaks, which contributes to differences in how dust storms develop and how the polar caps grow and shrink seasonally. This orbital eccentricity means that not all oppositions of Mars, when it comes closest to Earth, are created equal. During favorable oppositions that occur when Mars is near perihelion, the planet can approach Earth to within 35 million miles, making it appear especially large and bright. During less favorable oppositions, Mars may remain more than 60 million miles away, appearing noticeably smaller through telescopes. The Martian atmosphere is leaking into space. Even today, Mars continues to lose atmosphere to space, though at a much slower rate than occurred billions of years ago when the planet lost its magnetic field. NASA's MAVEN orbiter has measured the current rate of atmospheric escape and found that Mars loses about 100 grams of atmosphere every second, primarily through interactions with the solar wind. Over geological timescales, this ongoing loss is negligible compared to the massive atmospheric losses that occurred early in Mars's history. However, it does mean that any efforts to make Mars more habitable through terraforming would need to account for this continuing loss. The solar wind strips away lighter gases like hydrogen more readily than heavier ones like carbon dioxide, which is why Mars's atmosphere is now dominated by carbon dioxide while having very little water vapor or other lighter gases that might have been more abundant in the past. Mars has a day length that aids human adaptation. The similarity between a Martian sol and an Earth day is one of the many features that makes Mars a more attractive destination for human exploration than other planets. The extra 40 minutes means that human circadian rhythms would not need dramatic adjustment. Astronauts working on Mars missions would experience sunlight and darkness cycles very similar to those on Earth, helping them maintain normal sleep schedules. This contrasts sharply with the Moon. where a day lasts about 29 Earth days, creating 2 weeks of continuous sunlight followed by 2 weeks of darkness. Venus rotates so slowly that a day there lasts 243 Earth days. The similar day-night cycle on Mars would allow for work schedules, crop-growing cycles, and daily routines that closely mirror those on Earth, making Mars a more psychologically manageable environment for long-term human habitation. This simple coincidence of similar day lengths may prove to be one of the most important factors enabling future human settlement of Mars. Mars rocks have been found on Earth. Among the tens of thousands of meteorites that have fallen to Earth, scientists have identified more than 200 that almost certainly originated from Mars. These Martian meteorites were blasted off the red planet's surface by powerful asteroid impacts, traveled through space for millions of years, and eventually fell to Earth. We can identify them as Martian because gases trapped within them match the composition of Mars's atmosphere measured by Viking landers. These meteorites are incredibly valuable to scientists because they bring pieces of Mars to our laboratories, where we can analyze them with instruments far more sophisticated than those we can send to Mars. Some of these meteorites are very ancient, dating back more than 4 billion years to Mars's earliest history. Others are much younger, indicating relatively recent volcanic activity on Mars. Studying these fragments has taught us about Mars's interior composition, its volcanic history, and the history of water on the planet. One famous Martian meteorite found in Antarctica in 1984, designated ALH8 4001, sparked intense debate when some scientists proposed it might contain evidence of ancient microbial life in the form of tiny structures that resembled fossilized bacteria, though this interpretation remains highly controversial and is not widely accepted in the scientific community. The southern ice cap has a permanent cover of carbon dioxide ice. Unlike the northern ice cap, which is composed almost entirely of water ice beneath seasonal carbon dioxide frost, Mars's southern ice cap retains a permanent layer of carbon dioxide ice even in the summer. This permanent dry ice layer is about 26 feet thick and sits atop water ice below. The persistence of carbon dioxide ice at the South Pole results from that region's slightly lower temperatures and higher elevation compared to the north. This permanent dry ice cap gives the southern ice cap a distinctly different appearance from the northern one, and it raises interesting questions about Mars's climate history. The permanent carbon dioxide ice suggests that conditions at the South Pole have not warmed above the sublimation temperature of carbon dioxide, about -109 degrees Fahrenheit, for a very long time. Understanding why one polar cap retains permanent dry ice while the other does not helps scientists understand Mars's climate patterns and how heat and cold are distributed across the planet. Mars has ancient valley networks reminiscent of river systems, some of Boscate. The most striking evidence for ancient water on Mars comes from the valley networks that branch across the planet's southern highlands. These valleys, typically 1 to 3 miles wide and hundreds of miles long, show all the characteristics of river systems carved by flowing water. They start as narrow channels in the highlands and merge as they flow downhill, becoming wider and deeper exactly as rivers do on Earth. The valleys often show tributaries joining the main channel at acute angles, another signature of water erosion. Dating of the terrains surrounding these valleys suggests they formed during the Noachian period, more than 3.7 billion years ago, when Mars's climate was apparently very different from today. The source of the water that carved these valleys remains debated. Some scientists argue for precipitation, rain or snow falling from Martian clouds. Others suggest groundwater sapping, where water seeping from underground carved the valleys. Whatever the mechanism, these ancient valleys are compelling evidence that water once flowed across Mars in quantities and durations that could have supported life. The planet experiences strong seasonal changes. Because of its axial tilt and orbital position, Mars experiences seasons much like Earth, though they last approximately twice as long due to the Martian year being longer. Spring and summer in each hemisphere bring higher temperatures, retreating ice caps, and increased dust storm activity. Fall and winter bring cold, advancing frost, and calmer weather. However, Mars's elliptical orbit adds complexity to these seasonal patterns. Southern summer occurs when Mars is closest to the Sun, making it warmer but shorter than northern summer. This leads to more dramatic seasonal changes in the southern hemisphere. One of the most visible seasonal changes is the advance and retreat of the seasonal frost caps, which can extend down to latitudes of 45 degrees in winter before receding in spring. Dust storm activity also shows strong seasonal patterns, with the largest storms typically occurring during southern spring and summer when heating is most intense. These seasonal changes affect every aspect of the Martian environment, from temperature and pressure to wind patterns and dust distribution. Future human missions face many technological challenges. While sending humans to Mars has become a realistic goal, numerous technological hurdles must be overcome. The journey itself presents challenges, requiring life support systems that can function reliably for months. Radiation shielding to protect against cosmic rays and solar storms, and psychological support for crews confined in small spaces for extended periods. Once at Mars, astronauts will need habitats that can withstand dust storms, maintain comfortable temperatures despite the cold environment, and provide protection from radiation. They will need reliable sources of power, likely nuclear reactors or possibly solar panels combined with energy storage. Food will be a critical challenge, requiring either large stores of supplies brought from Earth or the development of agriculture on Mars using Martian resources. Water will need to be extracted from ice deposits and purified. Oxygen for breathing and rocket fuel for the return journey will ideally be produced on Mars rather than brought from Earth, requiring technologies that can harvest and process Martian atmospheric carbon dioxide and subsurface water. Communications with Earth will face time delays of 4 to 24 minutes, depending on the planet's positions, meaning that real-time mission control will be impossible, and crews must be able to handle emergencies independently. Each of these challenges is solvable, but solving all of them simultaneously represents an enormous undertaking. Mars has inspired dreams of terraforming, Some scientists and visionaries have proposed ambitious plans to transform Mars into a more Earth-like world through a process called terraforming. The concept involves thickening Mars's atmosphere, perhaps by releasing carbon dioxide trapped in the ice caps or subsurface, creating a greenhouse effect that would warm the planet. With higher temperatures and pressure, liquid water could exist on the surface. Introducing photosynthetic organisms might gradually produce oxygen over centuries or millennia. Eventually, if successful, Mars could become a world where humans could walk outside without spacesuits, where plants could grow in the open, and where a biosphere might flourish. However, terraforming Mars faces enormous practical and ethical challenges. The energy required would be staggering. We do not know if Mars contains enough volatile materials to create a thick atmosphere. The process would take centuries at minimum, possibly thousands of years. And philosophical questions arise about whether we have the right to transform another world, especially before we fully understand its current state, and whether it might harbor indigenous life. For now, terraforming remains firmly in the realm of speculation and long-term thinking, though it continues to inspire discussions about humanity's future as a spacefaring species. Small amounts of methane have been detected in Mars's atmosphere. One of the most intriguing and controversial discoveries about Mars is the detection of methane, a gas that on Earth is produced primarily by biological processes, though geological processes can also create it. Several missions have reported detecting tiny amounts of methane in the Martian atmosphere, though the measurements are at the very edge of detectability, and other missions have failed to find methane where and when it was expected. What makes methane particularly interesting is that it should not persist in Mars's atmosphere for very long. Ultraviolet light from the sun should break it down within a few hundred years. So if methane is present, something must be continuously replenishing it. Potential sources include underground reservoirs of ancient methane being released through cracks, ongoing geological processes like serpentinization, where water reacts with certain rocks, or possibly biological activity. The methane mystery remains unsolved, with scientists debating whether the detections are real and, if so, what they mean. Future missions may be able to trace methane plumes to their sources, potentially answering fundamental questions about whether Mars is geologically active or possibly even biologically active today. The dichotomy between Mars's hemispheres is one of its defining features. The dramatic difference between the heavily cratered, elevated southern highlands and the smooth, low-lying northern plains is called the Martian dichotomy, and it is one of the most prominent features of the planet. This hemispheric asymmetry exists at a fundamental level, affecting not just surface features but crustal thickness, geological age, and topography. Scientists have proposed several theories to explain how this dichotomy formed. One hypothesis suggests that a massive impact early in Mars's history, perhaps by an object 1/3 the mass of the Moon, could have blasted away the northern hemisphere's crust and left it permanently lower. Another theory proposes that internal processes, perhaps an early form of mantle convection or something resembling plate tectonics, thinned the northern crust. The mystery deepens because we see no clear evidence of a giant impact basin in the north, no obvious raised rim or circular pattern that such an enormous crater would likely create, though such features might have been erased over billions of years. Understanding the dichotomy is crucial for piecing together Mars's early history and how the planet evolved into its current form. Whatever process caused this dramatic division between north and south has shaped the planet's geology, climate, and water history for billions of years. As we consider the red planet and all its mysteries, let yourself drift into calm. Imagine standing on Mars, the red soil crunching softly beneath your feet, the distant sun casting long shadows across the ancient terrain. The sky above shifts from butterscotch to pink as dust hangs in the thin air. In the distance, Olympus Mons rises beyond the horizon, an invisible giant too large to perceive in its entirety. Somewhere beneath your feet lies the history of an entire world, billions of years of change recorded in layers of rock and dust. Water once flowed here, carving valleys and filling lakes. Now that water sleeps as ice, waiting patiently in the frozen ground and polar caps. The universe is patient. Mars waited billions of years for visitors from Earth to arrive, and it will wait billions more to see what becomes of human exploration and understanding. For now, Mars simply turns, day following night following day, its seasons marching in their steady rhythm, its winds sculpting dunes and carrying dust from one region to another, the cold and the silence, unchanged by the small rovers that crawl across its surface. You are part of this story now, having learned about this neighboring world. The atoms in your body were forged in stars, just like the iron that rusts in Martian soil. You are connected to Mars and all the cosmos through the elements that compose you. Let your breath settle into a gentle rhythm, like the rise and fall of Martian seasons. Let your thoughts become as calm as a windless Martian dawn. The red planet continues its endless orbit, and you continue your journey into sleep. Rest well, knowing that above us in the night sky, worlds wait to be explored, mysteries wait to be solved, and the universe carries on its slow, patient work of becoming, unfolding across deep time. Good night.